Welcome! In this session, we'll explore LeetCode problem number 1263, minimum moves to move a box to their target location. This problem challenges us to find the minimum number of moves required to push a box onto its target while navigating obstacles and constraints. Let's dive in and uncover the optimal strategies to solve this interesting problem. In this problem, you are given a grid that represents a game board where each cell can contain different elements. It might be empty, have an obstacle, contain a box, or mark the target location. Your goal is to determine the minimum number of moves required to push the box from its initial position to the target location. To move the box, you must push it, which means you need to be adjacent to the box and move in the direction of the push. However, there are some constraints. You can only move to empty cells, and you cannot pass through obstacles or the box itself. Additionally, you can freely move the player to any empty cell to position yourself for the next push. The objective is to minimize the number of pushes needed to get the box to the target. Let's look at an example to understand this better. Consider a grid where the walls are represented by hashtag, the target cell is T, the box is B, the starting position of the player is S, and dot represents empty spaces. In the first example, the output is 3, meaning the box can be moved to the target in 3 pushes. Here's how it works. First, the player moves to the left of the box to position themselves. Then, the player pushes the box one step to the left. After that, the player moves around to the top of the box, and finally, they push the box down to the target location. This sequence minimizes the number of pushes required, which is why the output is 3. In the second example, the output is -1, which indicates that it is impossible to push the box to the target. This happens because obstacles block all possible paths that the box could take to reach the target. Now, let's consider some constraints for the problem. The grid will always have dimensions between 1 and 20 for both rows and columns. Each cell in the grid will contain one of the following: an empty space, an obstacle, the player's starting position, the box, or the target. Importantly, there will always be exactly one box, one target, and one player on the grid. The player can move freely to any empty cell, but the box can only be pushed when the player is adjacent to it, and neither the box nor the player can pass through obstacles. If it's not possible to move the box to the target, you must return -1 as the result. To solve problem number 1263, minimum moves to move a box to their target location, we considered multiple approaches, each with its strengths and weaknesses. The challenge lies in the fact that the box cannot move on its own, it can only be pushed by the player. This means the player must navigate the grid, avoiding obstacles, to properly position themselves for each push. This creates a problem that combines pathfinding for the player with state management for the box, making the solution inherently complex. One straightforward way to attempt this problem is through a brute force approach. In this method, we simulate every possible sequence of player movements and box pushes. The player moves to a position adjacent to the box, pushes the box in every valid direction, and repeats the process until the target is reached. However, the major downside of this approach is its inefficiency. The state space grows exponentially with the size of the grid and the number of obstacles, leading to extremely poor performance and making it infeasible for larger grids. This motivates us to explore more optimized strategies. An optimized approach to solving this problem involves breadth-first search, or BFS, combined with a state-based representation. In this strategy, the problem is treated as a multi-dimensional shortest path problem, where the state represents both the positions of the box and the player at any given time. Specifically, a state is defined by 4 components: the box's position, represented as box_x, box_y, and the player's position, represented as player_x, player_y. To transition between states, the player first moves to a position adjacent to the box. From there, if the path is clear of obstacles, they can push the box in one of 4 directions: up, down, left, or right. The BFS algorithm is used to systematically explore all possible states, starting from the initial configuration and searching for the shortest path that leads to the target state, where the box's position matches the target. To ensure efficiency, we use a visited set to store all previously explored states, preventing redundant computations. Additionally, we observe that player movements only have a cost when required to push the box, and any attempt to push the box into an obstacle or invalid cell can be pruned immediately. This simplifies the problem into finding the shortest sequence of box pushes, with player movement as a subproblem. Analyzing the complexity of this approach, the time complexity can be approximated as O, m*n*p, where m and n represent the dimensions of the grid, and p is the maximum number of states that the player can reach within the grid. This makes the approach scalable for moderate grid sizes. Comparing the brute force method to the optimized BFS, the brute force strategy fails to prune invalid states, leading to an explosion in the number of paths explored, whereas the BFS approach systematically narrows down the search space. When considering depth-first search, or DFS, versus BFS, BFS is far better suited for shortest path problems. It explores all paths of a given length before moving on to longer paths, ensuring we find the shortest solution. On the other hand, DFS can get stuck exploring deep paths that are ultimately suboptimal. While a priority queue-based approach like a** search could theoretically improve performance, designing an effective heuristic for this problem is not straightforward. BFS, by contrast, is both simpler and guarantees correctness, making it a more practical choice. The BFS approach with state tracking was chosen because it offers an ideal balance of correctness, efficiency, and simplicity for this problem. By exploring all possible paths in increasing order of the number of pushes, BFS guarantees that the shortest solution is found. The use of a visited set ensures we avoid redundant computations and unnecessary state revisits, while the state representation captures the positions of both the player and the box, fully accounting for the constraints of the problem. This method is scalable for moderate grid sizes and effectively handles the complexities of navigating the player and pushing the box while avoiding obstacles. Overall, BFS with state tracking is a robust and reliable strategy that meets the requirements of the problem. In this problem, we are tasked with moving a box on a grid to a specified target position with the fewest possible moves. The catch is that the player can only push the box after positioning themselves correctly, which adds an extra layer of complexity. The grid also contains obstacles, which further restrict movement for both the player and the box. To solve this, we start by parsing the grid to determine the initial positions of the player, the box, and the target. Walls or obstacles are marked as impassable areas in the grid structure. Once the setup is complete, we use a breadth-first search, or BFS, to explore all valid states. Here, a state is represented as a combination of the box's position, box_x, box_y, and the player's position, player_x, player_y. We initialize the BFS with the starting state and a move counter set to 0. To avoid redundant work, we maintain a visited set that tracks all previously explored states, using their unique representation to ensure efficiency. Now, to push the box, the player needs to position themselves adjacent to it in the correct direction. To achieve this, we implement a helper function that uses another BFS to validate whether the player can navigate the grid to reach this required position. Once the player is in place, we consider all 4 possible directions for pushing the box: up, down, left, and right. For each direction, we calculate the new position of the box and ensure it remains within the grid and is not blocked by obstacles. Additionally, we must ensure the player can move to the position needed to execute the push. If these conditions are met, we proceed with a state transition. This involves updating the box's position, incrementing the move counter, and adding the resulting state to the BFS queue, provided it hasn't been visited before. After every successful push, we check whether the box has reached the target position. If it has, we immediately return the move counter as the result, since we've found the minimum moves required. If the BFS queue is emptied without reaching the target, it means the box cannot be moved to the target, and we return -1 to indicate failure. The key insight here is that the solution involves 2 levels of BFS. The first explores possible box movements, while the second ensures that the player can reach the position necessary to push the box. By representing each state as box_x, box_y, player_x, player_y, we ensure all relevant information is tracked efficiently. Additionally, the use of a visited set prevents revisiting states, optimizing the algorithm by avoiding redundant calculations. To implement this solution, we rely on key data structures. A queue is used for BFS to explore states level by level, guaranteeing that the shortest path is found. A hash set is employed to store visited states, enabling constant time lookups and eliminating duplicate processing. The grid itself is used to efficiently check boundaries and obstacles. For the complexity analysis, the time complexity depends on the grid size and the number of valid box positions. In a grid of size mxn, the time complexity is approximately O(m*n*k), where k represents the average number of valid states for the player. The space complexity is also O(m*n*k), to account for the queue and visited states. There are several edge cases to consider. If the box starts at the target, we return 0 immediately. If the box is surrounded by obstacles or the player cannot reach it, we return -1. BFS inherently ensures the shortest path is found, and all grid positions are validated to avoid out-of-bound errors during state transitions. Here, we begin by importing the Deque class from the Collections module, which we'll use for our breadth-first search, or BFS. Then, we define the min-pushbox function inside the solution class. The first step is to determine the dimensions of the grid by extracting the number of rows and columns. After that, we locate the initial positions of the player, the box, and the target by iterating through each cell in the grid. These positions are identified by their respective markers, S for the player, B for the box, and T for the target. Once their coordinates are stored, we define a helper function called can_move_to that will check if the player can move from a starting position to an ending position without stepping onto the box or crossing walls. It uses a BFS approach, starting with the given position and exploring all valid directions, while ensuring no cell is revisited or blocked by the box or obstacles. The can_move_to function continues here. It examines each potential move by calculating the new coordinates and ensuring they remain within bounds, are not walls, do not overlap with the box's position, and haven't already been visited. If a valid move is found, it's added to the queue for further exploration. This function ultimately returns whether the player can reach the specified destination. Next, we set up the main BFS to calculate the minimum number of pushes required to move the box to the target. The queue is initialized with a tuple containing the number of pushes, the box's position, and the player's position. We also maintain a visited set to avoid revisiting states. In the BFS loop, we process each state by dequeuing it, and if the box's current position matches the target, we return the number of pushes. Otherwise, we explore all possible directions by checking if the box can be pushed in each direction, ensuring the new positions are within bounds and free of obstacles. If the player can reach the position required to push the box, we add this new state to the queue and mark it as visited. Finally, if the queue is exhausted and the box cannot be moved to the target, we return -1 to indicate that it is impossible to achieve the goal. This ensures that we handle edge cases where the target is blocked or unreachable, completing our implementation of the min-pushbox function. Here, we start by defining our solution class and the min-pushbox method, which takes a 2D character array representing the grid. The first step is to determine the dimensions of the grid using rows and calls. Next, we initialize 3 arrays, player, box, and target, to store the coordinates of the player, the box, and the target, respectively. We then loop through each cell in the grid to locate these positions. When a cell contains S, it represents the player's starting position, so we store its coordinates in the player array. Similarly, B marks the box's position, and T marks the target's position. This setup is crucial for understanding where all the key elements are located as we proceed with the solution. Now, we define a helper method, can_move_to check if the player can move from a starting position to an ending position without stepping on the box. This method uses breadth-first search, BFS, to explore potential paths. A queue is used to hold the player's current position, and a set is used to track visited positions to prevent revisiting cells. For each position, we iterate over the 4 possible movement directions: right, down, left, and up. We calculate the new coordinates and ensure that the player stays within the grid boundaries, avoids walls, denoted by hashtag, and does not step onto the box's position. If the destination is reachable, the method returns true. This helper function is integral to our main algorithm as it ensures the player can move freely to push the box effectively. Now, we set up the BFS for the main algorithm to find the minimum number of pushes required to move the box to the target. We initialize a queue to store the state, which includes the number of pushes, the box's position, and the player's position. We also use a set to track visited states, ensuring we don't revisit the same configuration. While the queue is not empty, we process each state. If the box's current position matches the target, we return the number of pushes as the result. For each possible direction, we calculate the new positions of the box and the player, ensuring that the box stays within bounds, avoids walls, and the new state hasn't been visited. Additionally, we use the canMoveTo method to verify that the player can reach the position necessary to push the box in the intended direction. If all conditions are met, we add the new state to the queue. Finally, if the queue is exhausted and no valid solution is found, we return -1 to indicate that it's impossible to move the box to the target. This concludes our implementation. The algorithm ensures that all possible moves are explored systematically, while the use of visited states prevents unnecessary recomputation, keeping the solution efficient. This approach effectively combines BFS for both the player's movement and the overall box pushing process, solving the problem within the constraints. In this example, we start with a simple grid where the player is at position 4, 3, the box is at 2, 3, and the target is at 1, 1. Our goal is to move the box to the target position while making the minimum number of pushes. We initialize a BFS queue with the starting state 0 pushes, the box at 2, 3, and the player at 4, 3. We also maintain a visited set to track explored states, starting with 2, 3, 4, 3. During the first BFS iteration, we process the state where the box is at 2, 3, and the player is at 4, 3, with 0 pushes made so far. For each possible move of the box, we check if the player can reach the position required to push the box. When attempting to move the box up to 1, 3, the player needs to reach 3, 3. The can_move_to function confirms this is possible, so we enqueue the new state with 1 push, the box at 1, 3, and the player at 2, 3. Other directions for the box are either blocked or invalid, so we skip them. Next, we process the state where the box is at 1, 3, and the player is at 2, 3, with 1 push made. From here, we again consider all possible moves for the box. Moving the box left to 1, 2 requires the player to move to 1, 4. The can_move_to function confirms that the player can reach 1, 4, so we enqueue this new state with 2 pushes, the box at 1, 2, and the player at 1, 3. Moving further, we dequeue the state where the box is now at 1, 2, and the player is at 1, 3, with 2 pushes made. The only valid move for the box is to go left again to 1, 1, which is the target position. The player needs to stay at 1, 3 to make this push, which is validated by can_move_to. We enqueue the new state with 3 pushes, the box at 1, 1, and the player at 1, 2. Finally, we process the state where the box is at the target, 1, 1, and the player is at 1, 2. Since the box has reached the target, we output the minimum number of pushes required, which is 3. In this second example, we use a grid where the target location is blocked by walls, making it impossible to move the box to the target. The player starts at 4, 3, the box is at 2, 3, and the target is at 1, 1. As before, we initialize the BFS with a starting state of 0 pushes, the box at 2, 3, and the player at 4, 3. During the first BFS iteration, we process the state where the box is at 2, 3, and the player is at 4, 3, with 0 pushes. Checking the possible moves for the box, we see that moving the box up to 1, 3 requires the player to move to 3, 3. However, this path is blocked by a wall, hashtag, so the move is not valid. Similarly, all other directions for the box are either blocked by walls or invalid. With no valid moves for the box, the BFS queue becomes empty, and we conclude that it's impossible to move the box to the target. Therefore, the output for this example is -1, indicating no valid path exists. In this final example, we work with a larger grid where the player starts at 3, 1, the box is at 3, 3, and the target is at 1, 1. The BFS process begins with the initial state, 0 pushes, the box at 3, 3, and the player at 3, 1. By exploring valid moves for the box, we determine the minimum sequence of pushes required to reach the target. The box is pushed from 3, 3 to 2, 3, then to 1, 3, followed by 1, 2, and finally to the target, 1, 1. Each push is carefully checked to ensure the player can reach the required positions to make the moves, and the can_move_ to function validates player movement independently. By the end of the BFS process, we calculate that the minimum number of pushes required to move the box to the target is 4. This example highlights how BFS ensures the optimal solution by exploring states systematically, while the visited set prevents redundant computations. To begin analyzing the time complexity, we need to consider the key components of the algorithm. First, the outer BFS traversal explores all possible positions of the box and the player on the grid. Each state is represented as a pair of positions, one for the box and one for the player. The number of unique positions the box can occupy is limited by the total number of cells in the grid, which is m*n, where m is the number of rows and n is the number of columns. For each box position, the player can occupy any free cell, excluding walls and the box itself. This gives us an additional factor of m*n for the player's position. Multiplying these together, the total number of states in the outer BFS becomes m times n squared. Next, the inner BFS, which determines whether the player can move to a specific position to push the box, explores all accessible cells on the grid. In the worst case, this traversal is m*n. Since this check occurs for each potential box move, and there are 4 possible directions to push, the inner BFS contributes an additional factor of for m*n, which simplifies to m*n when considering constants. These two components form the foundation of the time complexity analysis. Now, combining these factors, the total time complexity of the algorithm emerges. The outer BFS has a state space size of m times n squared, representing all possible combinations of box and player positions. For each state, the inner BFS adds a cost of m*n, as it evaluates player movement possibilities. Multiplying these together, the overall time complexity becomes m times n squared, m*n, which simplifies to m times n cubed. Moving on to space complexity, the algorithm uses a visited set to track all explored, box_position, player_position, pairs. The size of this set is proportional to the total number of states, which is m times n squared. Additionally, the BFS queue for processing states also requires space proportional to the number of unique states, resulting in m times n squared space usage. Finally, the inner BFS, which evaluates player movement, uses its own queue and a visited set to track free cells, contributing an additional m*n space. These components together form the primary contributors to the algorithm's space requirements. Additionally, the grid itself requires storage space of m*n, as the grid structure needs to be maintained throughout the algorithm. Combining all these factors, the total space complexity can be summarized as m times n squared, for the visited set in BFS queue, plus m*n, for the inner BFS memory. Since m times n squared dominates, the overall space complexity of the algorithm is m times n squared. This means that while the algorithm is efficient in terms of avoiding exponential state explosion, it still requires a significant amount of memory for large grids. Understanding these space requirements helps us appreciate the trade-offs made by the solution design. The algorithm balances time and space efficiency while ensuring correctness within the problem constraints. Analyzing the best, average, and worst-case scenarios provides further insight into the algorithm's behavior. In the best case, the box is already at the target position, meaning no moves are required, and the algorithm terminates after the initial checks. In this scenario, the time complexity is 1. In the average case, the algorithm explores a smaller subset of the state space before finding a solution. The complexity in such cases lies between m times n squared and m times n cubed, depending on the distribution of obstacles and the structure of the grid. In the worst case, the grid layout forces the algorithm to explore all possible states, resulting in the full time complexity of m times n cubed. This worst-case scenario occurs in scenarios with highly unfavorable grid configurations, such as those with extensive obstacles or narrow pathways, which require exhaustive exploration of all states. Comparing this solution to a brute force approach highlights the significant optimization achieved. A naive method would attempt all possible sequences of box movements without leveraging BFS or tracking visited states, leading to exponential time complexity of O(4 to the power of k, where k represents the maximum number of moves. In contrast, the implemented solution optimizes this process by using a double-layer BFS. The outer BFS efficiently explores box states while the inner BFS handles player movement, ensuring that only valid states are considered. Furthermore, mathematical analysis confirms that the state space is bounded by O, open parenthesis m times n close parenthesis squared, with each state requiring up to O, m asterisk n, cells to be explored. This results in the derived time complexity of O, open parenthesis m times n close parenthesis cubed. By reducing redundant computations and focusing on valid states, the algorithm is efficient within the problem constraints. While further optimization might be possible, it would require reducing the state space or leveraging advanced heuristics. When tackling this problem, one of the most common mistakes is neglecting the interplay between the box's position and the player's position. Remember, the player must be adjacent to the box to push it, so it's critical to consider the player's reachability at all times. If you fail to track both positions simultaneously, your solution may end up incomplete or incorrect. Another frequent error is treating this as a simple shortest path problem. However, the movement of the box depends heavily on the player's accessibility, so a more nuanced approach is required. Using a dual-state BFS or A* search can help manage both the player and the box states effectively. Additionally, it's easy to overlook grid constraints, like obstacles or boundaries. Always ensure that moves are valid. This means staying within bounds and avoiding walls. Lastly, failing to track visited states, which represent combinations of the player's and box's positions, can lead to infinite loops or redundant calculations. To avoid this, use a visited set to store these combined states and prevent inefficiencies. Another area to be mindful of is how you represent states in your solution. Using overly complex or large data structures can slow down the algorithm unnecessarily. A more efficient approach is to represent states as simple tuples, such as box_x, box_y, player_x, player_y. This keeps the representation clear and minimizes overhead. For interviews, it's important to highlight your ability to design a solution that integrates two BFS searches, one for the box and another for the player. This dual-level state management demonstrates a strong grasp of the problem. Discussing the modeling of multi-agent movement problems is another great way to impress, as it shows you understand how the player's reachability directly impacts the box's movement. Be prepared to address edge cases, like when the box starts in the target position where the player is trapped and unable to move. Additionally, interviewers may look for optimization techniques, such as pruning strategies like early stopping when a solution is found or avoiding duplicate state exploration to improve efficiency. This problem also has several related problems that you might find helpful for additional practice. For example, LeetCode 773, the sliding puzzle, is another multi-state BFS challenge involving grid-based piece movements. Similarly, LeetCode 542, the 0-1 matrix, uses BFS or DFS to solve shortest path problems on a grid. LeetCode 1293, shortest path in a grid with obstacles elimination, combines grid traversal with state management, making it highly relevant. Lastly, LeetCode 505, the Maze 2, focuses on shortest path calculations within a grid while adhering to movement constraints. In terms of alternative approaches, you might consider using bidirectional BFS. Here, you search from both the initial state and the goal simultaneously, which can significantly reduce the search space. However, this comes with the trade-off of added complexity in synchronizing states between the two search directions. Another option is a asterisk search with heuristics, such as the Manhattan distance, to prioritize more promising states. This method can often be faster than BFS but requires careful design of the heuristic to ensure correctness and efficiency. Finally, another alternative approach is using DFS with backtracking. This method is useful when you need to explore all possible moves exhaustively. However, it's important to note that DFS with backtracking is generally inefficient for large grids due to its potential exponential time complexity. While it may be simpler to implement, it's not typically practical in interview scenarios because of its lack of scalability. For this reason, it's best suited for smaller scale problems or as a way to validate solutions in a controlled environment. Great job! Today, we addressed a challenging problem that tested our problem solving and algorithmic skills. Remember, grid-based problems like this often benefit from techniques like BFS or DFS. Keep practicing, and don't hesitate to revisit this problem for deeper understanding. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!